A more complex data structure, priority queues. Our primary goal in this book was expressed at the outset of the chapter. We seek algorithms that improve qualitatively on brute force search, and in general, we use polynomial time solvability as the concrete formulation of this. Typically, achieving a polynomial time solution to a non-trivial problem is not something that depends on fine-grained implementation details. Rather, the difference between exponential and a polynomial is based on overcoming higher-level obstacles. Once one has an efficient algorithm to solve a problem, however, it is often possible to achieve further improvements in running time by being careful with the implementation details, and sometimes by using more complex data structures. Some complex data structures are essentially tailored for use in a single kind of algorithm, while others are more generally applicable. In this section, we describe one of the most broadly useful sophisticated data structures, the priority queue. Priority queues will be useful when we describe how to implement some of the graph algorithms developed later in the book. For our purposes here, it is a useful illustration of the analysis of a data structure that, unlike lists and arrays, must perform some non-trivial processing each time it is invoked. The problem in the implementation of the stable matching algorithm, we discussed the need to maintain a dynamically changing set S, such as the set of all free men in that case. In such situations, we want to be able to add elements to and delete elements from the set S, and we want to be able to select an element from S when the algorithm calls for it. A priority queue is designed for applications in which elements have a priority queue or the key, and each time we need to select an element from S, we want to take the one with highest priority. A priority queue is a data structure that maintains a set of elements S, where each element V in S has an associated value key of V that denotes the priority of element V. Smaller keys represent higher priorities. Priority queues support the addition and deletion of elements from the set and also the selection of the element with the smallest key. Our implementation of priority queues will also support some additional operations that we summarize at the end of the section. A motivating application for priority queues, and one that is useful to keep in mind when considering their general function, is the problem of managing real-time events, such as scheduling of processes on a computer. Each process has a priority or urgency, but processes do not arrive in order of their priorities. Rather, we have a current set of active processes, and we want to be able to extract the one with the currently highest priority and run it. We can maintain this set of processes in a priority queue with the key of a process representing its priority queue, its priority value. Scheduling the highest priority process corresponds to selecting the element with the minimal key from the priority queue. Concurrent with this, we will also be inserting new processes as they arrive according to their priority values. How efficiently do we hope to be able to execute the operations in a priority queue? We will show how to implement a priority queue containing at most n elements at any time so that elements can be added and deleted and the element with minimal key selected in big O of log n time per operation. Before discussing the implementation, let us point out a very basic application of priority queues that highlights why big O of log n time per operation is essentially the right bound to aim for. 2.11 A sequence of big O of n priority queue operations can be used to sort a set of n numbers. Proof: set up a priority queue H and insert each number into H with its value as a key. Then extract the smallest number one by one until all numbers have been extracted. This way, the numbers will come out of the priority queue in sorted order. Thus, with a priority queue that can perform insertion and the extraction of minima in big O of log n per operation, we can sort n numbers in big O of n log n time. It is known that in a comparison-based model of computation, when each operation accesses the input only by comparing a pair of numbers, the time needed to sort must be at least proportional to n log n. So 2.11 highlights a sense in which big O of log n time per operation is the best that we can hope for. We should note that the situation is a bit more complicated than this. Implementations of priority queues more sophisticated than the one we present here can improve the running time needed for certain operations and add extra functionality. But 2.11 shows that any sequence of priority queue operations that results in the sorting of n numbers must take time at least proportional to n log n in total. A data structure for implementing a priority queue. We will use a data structure called a heap to implement a priority queue. Before we discuss the structure of heaps, we should consider what happens with some simpler, more natural approaches to implementing the functions of a priority queue. We could just have the elements in a list and separately have a pointer labeled min to the one with minima key. This makes adding new elements easy, but extraction of the minima hard. Specifically, finding the minima is quick. We just consult the min pointer, but after removing this minima element, we need to update the min pointer to be ready for the next operation, and this would require a scan of all elements in big O of n time to find the new minima. This complication suggests that we should perhaps maintain the elements in the sorted order of the keys. This makes it easy to extract the element with smallest key. But now, how do we add a new element to our set? Should we have the elements in an array or a linked list? Suppose we want to add s with key value key of s. If the set s is maintained as a sorted array, we can use binary search to find the array position where s should be inserted in big O of log n time. But to insert s in the array, we would have to move all later elements one position to the right. This would take big O of n time. On the other hand, if we maintain the set as a sorted doubly linked list, we could insert it in big O of 1 time into any position. But the doubly linked list would not support binary search, and hence we may need up to big O of n time to find the position where s should be inserted. The definition of a heap. So in all these simple approaches, at least one of the operations can take up to big O of n time, much more than the big O of log n per operation that we are hoping for. This is where heaps come in. The heap data structure combines the benefits of a sorted array and a list for purposes of this application. Conceptually, we think of a heap as a balanced binary tree as shown on the left of figure 2.3. The tree will have a root and each node have up to 2 children. a left and a right child. The keys in such a binary tree are said to be in heap order if the key of any element is at least as large as the key of the element at its parent node in the tree. In other words, heap order is that for every element v at a node I, the element w at i's parent satisfies that the key of w is less than or equals to key of v. In figure 2.3, the numbers in the nodes are the keys of the corresponding elements. Before we discuss how to work with a heap, we need to consider what data structure should be used to represent it. We can use pointers. Each node at the heap could keep the element it stores, its key, and 3 pointers pointing to the 2 children and the parent of the heap node. We can avoid using pointers. However, if about n is known in advance on the total number of elements that will ever be in the heap at any one time, such heaps can be maintained in an array H indexed by I equals to 1 to 3 until n. We will think of the heap nodes as corresponding to the positions in this array. Each of 1 is the root, and for any node at position I, the children are the nodes at position left child of I equals to 2i and the right child of I equals to 2i plus 1. So the 2 children of the root are at positions 2 and 3, and the parent of a node at position I is at position parent of I equals to the floor function of I over 2. If the heap has little n, which is less than capital N, the elements at some time, we will use the first little n positions of the array to store the n heap elements and use length of capital H to denote the number of elements in capital H. This representation keeps the heap balanced at all times. See the right-hand side of figure 2.3 for the array representation of the heap on the left-hand side. Implementing the heap operation. The heap element with the smallest key is at the root, so it takes big O for one time to identify the minimal element. How do we add or delete heap elements? First, considering adding a new heap element v, and assume that our heap H has little n, which is less than capital N elements so far. Now it will have n plus 1 elements. To start with, we can add the new element v to the final position I equals to n plus 1 by setting h of I equals to v. Unfortunately, this does not maintain the heap property, as the key of element v may be smaller than the key of its parent. So we now have something that is almost a heap, except for a small damaged part where v was pasted on at the end. We will use the procedure heapify up to fix our heap. Let j equals to parent of I, which is equals to the floor functions of I over 2, be the parent of the node I, and assume that h of j is equals to w. If key of v is less than key of w, then we will simply swap the positions of v and w. This will fix the heap property at position I, but the resulting structure will possibly fail to satisfy the heap property at position j. In other words, the side of the damage has moved upward from I to j. We thus call the process recursively from position j equals to parent of I to continue fixing the heap by pushing the damaged part upward. Figure 2.4 shows the first two steps of the process after an insertion. To see why heapify works, eventually restoring the heap order. It helps to understand more fully the structure of our slightly damaged heap in the middle of this process. Assume that H is an array and V is the element in position I. We say that H is almost a heap with the key of H of I too small. If there is a value alpha greater than or equals to key of V, such that raising the value of key of V to alpha would make the resulting array satisfy the heap property. In other words, element V in H of I is too small, but raising it to alpha would fix the problem. One important point to note is that if H is almost a heap with the key of the root, i.e. H of 1, too small, then in fact it is a heap. To see why this is true, consider that if raising the value of H of 1 to alpha would make H a heap, then the value of H of 1 must also be smaller than both its children, and hence it already has the heap order property. 2.12 A procedure heapify up of H and I fixes the heap property in big O of log I time, assuming that the array H is almost a heap with the key of H of I too small. Using heapify up, we can insert a new element in a heap of n elements in big O of log n time. Proof. We prove the statement by induction on I. If I is equals to 1, there is nothing to prove, since we have already argued that in the case H is actually a heap. Now consider the case in which I is greater than 1. Let V equals to H of I, J equals to parent of I, W equals to H of J, and beta equals to key of W. Swapping elements V and W takes big O of 1 time. We claim that after the swap, the array H is either a heap or almost a heap with the key of H of J, which now holds V too small. This is true as setting the key value at node J to beta would make H a heap. So by the induction hypothesis, applying heapify up of J recursively will produce a heap as required. The process follows the tree path from position I to the root, so it takes big O of log I time. To insert a new element in a heap, we first add it as the last element. If the new element has a very large key value, then the array is a heap. Otherwise, it is almost a heap with the key value of the new element too small. We use heapify up to fix the heap property. Now consider deleting an element. Many applications of priority queues don't require the deletion of arbitrary elements, but only the extraction of the minima. In a heap, this corresponds to identifying the key at the root, which will be the minimum, and then deleting it. We will refer to this operation as extract the min of H. Here we will implement a more general operation delete of Hi, which will delete the element in position I. Assume the heap currently has n elements. After deleting the element H of I, the heap will have only n-1 elements. And not only is the heap order property violated, there is actually a hole at position I, since H of I is now empty. So, as a first step, to patch the hole in H, we move the element W in position N to position I. After doing this, H at least has the property that its n-1 elements are in the first n-1 positions, as required, but we may well still not have the heap order property. However, the only place in the heap where the order might be violated is position I, as the key of element W may be either too small or too big for the position I. If the key is too small, that is, the violation of the heap property is between node I and its parent, then we can use heapify up of I to re-establish the heap order. On the other hand, if key of W is too big, the heap property may be violated between I and one or both of its children. In this case, we will use a procedure called heapify down. Closely analogous to heapify up, that swaps the element at position I with one of its children and proceeds down the tree recursively. Figure 2.5 shows the first step of this process. Assume that H is an array and W is the element in position I. We say that H is almost a heap with the key of H of I too big. If there is a value alpha which is less than or equals to key of W such that the lowering the value of key of W to alpha would make the resulting array satisfy the heap property. Note that if H of I corresponds to a leaf in the heap, i.e. it has no children, and H is almost a heap with H of I too big, then in fact H is a heap. Indeed, if lowering the value of H of I would make H a heap, then H of I is already larger than its parent, and hence it already has the heap order property. (2.13) Procedure heapify down of Hi fixes the heap property in big O of log n time, assuming that H is almost a heap with the key value of H of I too big. Using heapify up or heapify down, we can delete a new element in a heap of n elements in big O of log n time. We prove that the process fixes the heap by reverse induction on the value I. Let n be the number of elements in the heap. If 2i is greater than n, then as we just argued above, H is a heap, and hence there is nothing to prove. Otherwise, let J be the child of I with a smaller key value, and let W equals to H of J. Swapping the array element W and V takes big O of 1 time. We claim that the resulting array is either a heap or almost a heap with Hj equals to V too big. This is true as setting key of V equals to key of W would make H a heap. Now J is greater than or equals to 2i, so by the induction hypothesis, the recursive call to heapify down fixes the heap property. The algorithm repeatedly swaps the element originally at position I down, following a tree path, so in big O of log n iterations, the process results in a heap. To use the process to remove an element V equals to Hi from the heap, we replace Hi with the last element in the array, H of n equals to W, If the resulting array is not a heap, it is almost a heap, with the key value of h of I either too small or too big. We use heapify down or heapify up to fix the heap property in big O of log n time. Implementing priority queues with heaps. The heap data structure with the heapify down and heapify up operations can efficiently implement a priority queue that is constrained to hold at most n elements at any point in time. Here we summarize the operations we will use. Start heap of n returns an empty heap h that is set up to store at most n elements. This operation takes big O of n time, as it involves initializing the array that will hold the heap. Insert of h v inserts the item v into heap h. If the heap currently has n elements, this takes big O of log n time. Find min of h identifies the minimum element in the heap h, but does not remove it. This takes big O of 1 time. Delete of hi deletes the element in heap position I. This is implemented in big O of log n time for heaps that have n elements. Extract the min of h identifies and deletes an element with minimal key value from a heap. This is a combination of the preceding two operations, and so it takes big O of log n time. There is a second class of operations in which we want to operate on elements by name rather than by their position in the heap. For example, in a number of graph algorithms that use heaps, the heap elements are nodes of the graph with key values that are computed during the algorithm. At various points in these algorithms, we want to operate on a particular node regardless of where it happens to be in the heap. To be able to access given elements or of the priority queue efficiently, we simply maintain an additional array position that stores the current position of each element, each node in the heap. We can now implement the following further operations. To delete the element v, we apply delete of h and the position of v. Maintaining this array does not increase the overall running time, and so we can delete an element v from a heap with n nodes in big O of log n time. An additional operation that is used by some algorithms is change key of h, v, and alpha, which changes the key value of element v to key of v equals to alpha. To implement this operation in big O of log n time, we first need to be able to identify the position of element v in the array, which we do by using the array position. Once we have identified the position of element v, we change the key and then apply heapify up or heapify down as appropriate.